Okay, my name is Kobe Pasquale, and I'm going to talk about a paper done by Sebastian Thrun back in 1995 called An Approach to Learning Mobile Robot Navigation. So I'm going to go over a quick overview of what I'm going to talk about. First, the introduction of the paper and the contents of the paper. Then I will go into the application summary, which is where I talk about the major contribution of this paper, which is called the EBNN algorithm and the components in it. And then I'll go over some of the physical experiments that were done here. The next thing I'm required to talk about is the internal evaluation. So I'm going to give you a list of criteria, and I'm going to discuss those in regards to how this paper was written. Then the application evaluation, where I'm going to talk about a tour guide robot. I'm going to talk about what this approach does and does not have in regards to a tour guide robot, and I'll conclude the suitability of what this approach has, how it will work with the tour guide robot. So the goal in this is to design an algorithm that allows a robot to perform a variety of tasks independently and efficiently. In the real world, there are many constraints that don't really allow this task to be trivial. The reason for this is because in real world environments, they're very unknown and very random. In other words, they're very large. So even if the environment was known, they're so big and very complex that to be able to hand code everything would be incredibly difficult and very expensive. And even if you had the resources to do that, it would be so computationally expensive that it would not effectively do anything. So the algorithm that is employed here is called the EBNN algorithm, which is the explanation-based neural network. So the author describes a new algorithm using multiple machine learning techniques. There's three types that are involved: inductive learning, which is a neural network; the analytical learner, which is an explanation-based learning technique; and then the reinforcement learning, which is called Q-learning here. So an overview of what a neural network is. It is a supervised learning technique, which means when you in the training phase, whenever it spits out an answer based on your inputs, you give it the answer and it can self-correct to try to make a better output the next time. The components, for instance, in this basic neural network here are the input units, which is the input nodes here, just whatever is coming from your environment, your hidden units, and your output. The nodes, or the lines here that are connecting these nodes are called the weights. The weights are some sort of function that will be employed onto the input unit. So you say you have an input here, it goes through a weight, which means it's being manipulated by some sort of formula. It gets to a hidden unit, it's manipulated again, and then finally it's manipulated through one more set of weights to get an output. And in this case, we're using a backpropagation algorithm. So whenever you get the output, you tell it, hey, this is what it should have been, and it can calculate the error and then go back through the neural network and update those weights so that in future it should find a better model for whatever you're trying to predict. The other two things are EBL, which is explanation-based learning. What this, in an overview of this, is it just requires a domain theory. So in other words, before it can actually do its job, it needs to have some sort of prior knowledge about the environment. It needs to know something like a set of rules of what leads to a prediction. And what it does is generalize a set of rules. So in essence, what it does is it takes a domain theory, it generalizes the things in the domain theory, which means that it can improve the domain theory. And the Q-learning is the reinforcement learning portion of this, and it's a reward system. So basically, if the robot does something good, it gets rewarded for it. If it does something bad, it gets a negative reward or a penalty. And the system basically sets up a value network to where you always pick the best action. And a good way to describe how reinforcement learning works is a human playing a video game. Let's say you've never played before, you get to the end of a level, you win, you know, oh wow, I need to do that again, whatever I can do to win again. Or if I die, you know, when I get to that point again, I need to avoid whatever I did that time. So the physical experiments were with a Xavier robot, which had 24 sonar sensors to detect distance, and this went all the way around it. It had a laser rangefinder, which is just right in front of it, but it was very precise, and it had a pan-tilt camera on top of it, which it could locate things in their color, which is important because the goal of this experiment was to set this robot in an arbitrary location within an environment, and the goal was for it to map and navigate to a green target where it was arbitrarily placed in the room. So in between each learning episode, it would learn. In other words, it would either fail or get to the goal, and then it would start over. They would randomly place it again, and they would move the marker again. And they did this several different times to try to learn this equation. And after the learning phase, they went through a testing phase where they introduced obstacles into locations in the room. And using this EBNN algorithm, the robot was able to find the marker upwards of 90% of the time, even when the obstacles were introduced, and it did never see that when it was learning in the training phases. And here is just an overview of one of the experiments that went 20 episodes. So if you look at the first episode, second episode, and the sixth episode on the top, you can see that the robot failed to find the marker. But by 18, 19, and 20, it was successfully getting to its location every time. So it only took about 20 episodes, and these episodes were pretty short. They were about 11 actions on average, and the actions were chosen every 3 seconds. So this was very quick. Now moving on to the internal evaluation, I'm just going to read off some of these and sort of talk about how they pertain to this paper. Is this approach relevant today? I thought this was a good criteria to use because it's such an old paper. This was almost 22 years ago that this paper was published, but it still is very relevant because we're in such an age now where we're using things like this, where we're learning machine learning to be able to employ things in robots, to be able to do things that we wouldn't be able to explicitly tell them how to do. Was it efficient? Absolutely it was. In the paper, they noted that they only needed 10 minutes of robot operation time to actually learn the environment. So within start and finish, within 10 minutes, this robot was able to take all of the information that it needed and then do everything that it needed to do to avoid these obstacles and get to where it needed to go. Which is important because one of the things that the paper stated was it needed to be efficient. Was the contribution practical? Even though it was a very small scale type of experiment, in the world that we're in today, it is absolutely practical. If you think that obviously 22 years later, we're a little bit more advanced than we were then, but today there's a big thing of the self-driving cars. Well, this is sort of a similar problem because self-driving cars need to be able to do something like this, but you can't just hand code everything that a self-driving car is needed to do. It needs to be able to navigate itself throughout a world, and it needs to learn quickly. And hopefully those are pre-learned, but it's very similar in what it's supposed to do. Were the experiments thorough? This was a relevant criteria, I thought, because for the actual physical experiments, they were pretty limited. There was only about half to a 3/4 page actually discussing what was going on with the physical experiments. It seemed that this paper was more wanting to just let you know that their algorithm worked rather than giving a step-by-step evaluation of how it worked. But they did get good results accordingly. They said, like we talked a minute ago, it only took them 10 minutes to learn, and on average they learned in less than 19 episodes. And again, 19 episodes, 11 actions, 3 seconds for each action. So pretty quickly is how quickly these things learned. Do the results support the hypothesis? Well, the hypothesis was implicit, saying that they wanted to find an algorithm that was able to control a robot to be able to navigate on its own, or to navigate efficiently, and to be able to learn on its own. And both of those things were employed here. It was dropped in an environment that it had no prior knowledge, and it was able to get where it needed to go in a very quick manner, especially in the testing phases when they weren't actually learning it anymore, learning the learner. Independence of approach. Again, how independent was this approach? I sort of covered that a minute ago on accident, and the result support the hypothesis, but what the goal was for it to find where it needed to go. But what was pretty interesting is how independent this actually was in doing so. And there were two different ways that they did the physical experiments that I didn't have time to talk about, but that was they did where they gave no information to the robot and then they gave some information to the robot, excuse me. Well, in the instances where they didn't give any information to the robot, it had to learn on the fly. It was always successful in finding where it needed to go. So it was very so much independent in finding its path. Okay, on to the application evaluation in regards to a tour guided robot. The goal for this is for a robot to independently conduct a tour for a group of people or students around the OU campus, particularly the CS campus. The things that it needs to be able to do is map an environment and be able to self-navigate around this map. It needs to be able to avoid obstacles, so it can't run into anything, it can't run into people, and obviously it can't fall down stairs. It needs to be able to locate a target and find a plan to approach it. So it needs to find, let's say, we can go off the CS campus a little bit. We can say from Devon to the football stadium. If it has a floor plan, yes, it can map itself all the way to the football stadium, but there might be intermediate landmarks that it would be using that it could find a plan to get there. It needs to be able to notify participants about certain landmarks. So it wouldn't be much of a tour guide if it couldn't give information about the buildings around campus. And the software would not be able to be hard-coded just because the environment, as we talked about, was so large that it just wouldn't be feasible. So here are some characteristics that the approach does not really contain that in regards to this paper. Obviously, there was no voice capability. It wouldn't be able to talk to anyone. Touch capability, if let's say a tour guide robot was able to move things or open an elevator door, in this situation it wouldn't have that kind of functionality. It also wouldn't be able to detect whether there was stairs or not. I mean, you probably could use that camera for that, but in this case it's not what it had, and it did not have floor sensors to be able to notice if there was a floor underneath it. And probably the biggest thing that it would fail at is not being able to avoid non-static obstacles. Though it did have an obstacle avoidance routine, it likely would not have done very well with people moving around, as it mapped out things initially and then just sort of moved accordingly. It was a very reactive robot. Like I said, it could choose an action every 3 seconds. So basically, it goes 3 seconds and then something happens, does something else every 3 seconds. So there's not really much planning involved, and for such a large-scale problem, this probably wouldn't be very effective. The things that it does contain, it can self-navigate, even though there's no planning involved. As long as it has something that it can see or it can locate, then it can move toward it. It can create a map of its environment. So things that are static would be easy, as we saw in the experiment. So if it was, let's say, mapping the Devon atrium at 4 in the morning when there's no one in there, it could do well in moving around. So it would be able to move around tables. It could do whatever it needed to do to avoid obstacles. It could locate a target. As we said, that's how it moved. It would watch something, and that's how it decided how to get there. The software obviously was independent, so it wasn't hard-coded. And it can ride in an elevator if the door is open, I guess. So the suitability of this would actually be pretty relevant if you were going to build a tour guide robot to some extent. It can't handle all the tasks to be able to actually be a tour guide, but it has a lot of the important parts of being a tour guide. And in other words, it could, if you gave it the landmarks to look for and sort of knowledge of the environment prior to starting this experiment, it would be able to navigate to each one on its own after some training, add some speakers. Every time you hit an environment, boom, no problem. So in conclusion, Thrun used several machine learning properties to create this EBNN algorithm, and he was able to drop a robot in an environment where no prior knowledge of the environment was known, and it was still successfully able to map the environment and navigate around obstacles and through the environment to find a target. And this technique, in my opinion, would be largely useful for a two-guided robot if the space was smaller, say, just the Devon atrium. And that's it.